December 1979. A secure subterranean computing facility 50 kilometers outside Moscow. The air is still, cool, and smells of ozone, machine oil, and anxious sweat. The only sounds are the hum of ventilation, the whir of tape drives, and the rhythmic chatter of a line printer. A group of men in grey lab coats stand in a tense semicircle, their faces etched in the pale, flickering light of a mainframe console. They are not soldiers, but their work will decide the fate of armies. In the hands of their superior, Colonel General of the Engineering Service, rests a slim, thermofaxed report, smuggled through layers of iron curtain secrecy. Its contents are not battle plans, but benchmarks. He reads a single line aloud, his voice flat, devoid of its usual authority. Central Data Corporation, 7600. A glacial silence follows. One scientist, a lead designer of the Soviet Union's most advanced BSM-6 computer, closes his eyes. His machine, a masterpiece of Soviet electronics, a sprawling complex of vacuum tubes and early transistors, is capable of 1 million operations per second. On a good day, the number hangs in the chilled air, 36 to 1. It is not a difference of degree, but of kind. It is a chasm. Outside, in the frozen darkness, trains are moving, divisions are assembling. In weeks, Soviet troops will cross the Amu Darya into Afghanistan, a war planned with political certainty, but now shadowed by a terrifying, newfound technological uncertainty. The war would be fought with tanks and helicopters, but it would be decided by numbers like these, numbers that these men now understood their nation could not calculate. The Cold War, for all its iconic imagery of missile parades and proxy battlefield clashes, was fundamentally a war of mathematics. It was a silent, relentless contest of equations. The race to the moon, the efficiency of a nuclear warhead, the flight path of an intercontinental ballistic missile, the stealth of a submarine. Each was a universe of variables waiting to be solved. Victory would not necessarily go to the side with the most steel, but to the side that could most accurately simulate reality inside a machine before committing to it in the physical world. This was the birth of the supercomputer, and it was a birth that took place almost exclusively in the West. In the United States, the drive was led by a singular, almost monastic figure, Seymour Cray. Working in the isolation of Chippewa Falls, Wisconsin for Controlled Data Corporation, so CDC, Cray embodied a fusion of artistic vision and engineering rigor. His goal was transcendent simplicity, build the fastest computer in the world. To do this, he had to reinvent everything. The CDC 6600, released in 1964, was not just faster, it was architecturally revolutionary. It used a RISC-like design philosophy, dedicating specialized peripheral processors to handle input/output, freeing the central processor to do nothing but compute. It was cooled by Freon, its circuits meticulously hand-wired to minimize signal delay. It was, in the parlance of the time, a supercomputer. It was so fast that IBM, the industry giant, was investigated for antitrust violations, accused of trying to stifle CDC because it couldn't compete technologically. The successor, the CDC 7600, unveiled in 1969, was another leap. It achieved its staggering speed, that fateful 36 megaflops, through a combination of scalar and vector processing, and an even more obsessive focus on compact, efficient circuitry and cooling. These machines were not general-purpose business tools, they were national strategic assets. They were installed at Lawrence Livermore and Los Alamos National Laboratories, where they ran simulations of thermonuclear explosions, rendering physical testing increasingly obsolete. They modeled aerodynamics at NASA, cracking problems of re-entry heating and hypersonic flight. They broke cryptographic codes at the NSA. Military-industrial complex, the supercomputer became a force multiplier of incalculable power, a crystal ball that could foresee the performance of a weapon system with a degree of fidelity previously unimaginable. Meanwhile, in the Soviet Union, computation followed a different parallel path. By the 1960s, this stance had reversed under military pressure, and computing became a top priority, but within a closed, isolated, and bureaucratically shackled system. Soviet computer science produced brilliant theorists and capable machines. The BSM series, developed under the leadership of Sergei Lebedev, were formidable achievements. The BSM-6, operational by 1967, was the pinnacle of Soviet computing for over a decade. It was fast, reliable by Soviet standards, and used in critical aerospace and defense projects. But the system's fatal flaws were structural. Soviet industry was optimized for heavy machinery and mass production, not for the rapid, miniaturized innovation of microelectronics. The production of integrated circuits was plagued by quality control issues. The culture of secrecy between competing design bureaus stifled the open exchange of ideas that fueled Western advances. Most crucially, the entire ecosystem, from hardware to programming languages to applications, was a closed loop. Soviet scientists had no direct access to the bleeding-edge work of Cray or his competitors. They saw shadows, rumors, and the occasional sanitized technical paper. Their understanding of the gap was for years theoretical. They suspected they were behind. They did not know they were being lapped. This was the state of play as the 1970s unfolded. In America, the Silicon Revolution was accelerating. In the USSR, the Politburo demanded parity, issuing decrees for faster machines, while the ground floor reality of material science and manufacturing lagged hopelessly behind. The Soviet war machine was vast, its weapons often brutally effective through ruggedness and simplicity. But in the silent rooms where the future was calculated, a quiet desperation was beginning to build. The battlefield was shifting from the steppes to the silicon wafer, and the Red Army, for all its tanks, was advancing into a territory it did not understand. The strategic implications of this computational divide were profound and multifaceted. Instead of building 10 prototypes of a new fighter jet and testing them to destruction in wind tunnels and flight tests, you could build one virtual model and simulate tens of thousands of flight hours, exploring every extreme of its performance envelope. You could model the precise effects of a new shaped charge warhead against Soviet tank armor, iterating the design digitally until the mathematics promised a kill. This drastically reduced development time, cost, and risk. It allowed for leaps in complexity and performance that were simply unattainable through trial and error alone. The F-117 Nighthawk stealth fighter, born in the late 1970s, was a child of this process. Its faceted design was the only shape supercomputers of the era could accurately model for radar cross-section calculations. In the Soviet Union, the opposite was true. The design process remained intensely physical and iterative. To test a new missile guidance system, you had to build it, fit it to an airframe, and fire it, often repeatedly, at great expense. Aerodynamic refinements for aircraft or helicopters relied more on intuition, scale models in wind tunnels, and the courage of test pilots. This fostered a different kind of engineering genius, robust, pragmatic, and brilliant within constraints, but it was inherently slower and less precise. When a Soviet scientist looked at a blueprint, he saw an object to be constructed. When his American counterpart looked at a design file, he saw a set of equations to be solved, a behavior to be predicted. This was the core of the gap. It was a divergence in the very conception of creation. The realm of nuclear strategy exemplified this chasm most terrifyingly. The United States, through Livermore and Los Alamos, used machines like the CDC 7600 to run sophisticated hydrodynamics code simulating the microseconds of a thermonuclear implosion. This allowed for the development of smaller, lighter, more efficient, and more predictable warheads. It enabled concepts like multiple independently targetable re-entry vehicles, MIRVs, packing multiple warheads onto a single missile, each requiring precise, miniaturized nuclear packages. The Soviet nuclear establishment, centered at Arzamas-16, had its own computational resources, but the lack of raw speed and sophisticated simulation software meant their designs had to be more conservative, often larger, and required more live testing to validate. The quest for parity in the arms race was thus not just a matter of will or industrial capacity. It was a race against an invisible mathematical clock that ticked faster in California than it did in Siberia. This technological environment set the stage for the geopolitical decisions of the late 1970s. In Washington, confidence in technological superiority informed a more aggressive stance. It allowed for the development of weapons systems that seemed to leapfrog a generation, sowing doubt in Moscow. In Moscow, the Politburo, led by an aging Brezhnev, felt this pressure acutely. Their intelligence services reported on these advancements, but the full, horrifying scale of the computational underpinning was often obscured or misunderstood. The Soviet response was typically twofold: a redoubling of espionage efforts to steal Western secrets, and massive state investment in domestic projects meant to close the gap, like the Elbrus supercomputer project. These efforts were hampered by the same systemic issues that created the lag. It was against this backdrop of simmering technological anxiety that the Soviet leadership made the decision to intervene militarily in Afghanistan in December 1979. The political rationale was clear: prevent the collapse of a communist ally, secure the southern border, and check American influence. But militarily, it was a commitment born of a classic brute force worldview. It was an operation planned with maps, political directives, and an overwhelming faith in the massed firepower of the Soviet military. There was no supercomputer in Moscow running a complex simulation of a counterinsurgency in mountainous terrain. There was no algorithm modelling the sociological impact of a foreign occupation on a tribal society, or the logistical nightmare of supplying a mechanized army through the Salang Pass. The decision was a product of political calculus and imperial inertia, utterly divorced from the new age of predictive analysis that was guiding its primary adversary. The Soviet army would cross the bridge at Termez, armed with the tools of a previous era's warfare, commanded by a system that was just beginning to comprehend how far behind it had fallen in the era of silicon. The men and women in the grey lab coats of the Soviet Academy of Sciences were not incompetents. They were often world-class theorists operating under a pall of immense pressure and profound isolation. Their lives were a paradox of privilege and constraint. They lived in closed cities like Zelenograd, the intended Soviet Silicon Valley, or within secure academic enclaves, enjoying better housing, food, and consumer goods than the average citizen. But their world was bounded by barbed wire, secrecy oaths, and the ever-present oversight of the KGB's Scientific Counterintelligence Directorate. Their work was defined by a crushing duality. On one hand, they were driven by genuine scientific passion and patriotic fervour, a desire to prove the superiority of the socialist system through technical achievement. On the other, they were hamstrung by that very system. Innovation was top-down, dictated by 5-year plans and bureaucratic committees. A brilliant circuit design meant nothing if the semiconductor factory in Minsk could not produce the chips to the required purity and tolerance. Access to information was their greatest hunger and their greatest frustration. Western technical journals arrived months late, heavily censored. Attendance at an international conference was a rare prize, a chance to glimpse the outside world, but every conversation was guarded, every question measured against what it might reveal about Soviet weaknesses. The psychological toll was immense. For the elite who understood the true scale of the gap, like the BSM-6 team reading the CDC 7600 report, it fostered a specific kind of despair. They could diagnose the illness but were forbidden from prescribing the true cure. Open exchange, market-driven competition, and a fundamental restructuring of the industrial base. Instead, they were ordered to innovate, to produce a Soviet response with inadequate tools. This led to ingenious, sometimes bizarre workarounds. When high-quality integrated circuits were scarce, they might design a processor that used fewer of them, sacrificing performance for buildability. Software developers lacking advanced compilers wrote critical code directly in machine language, a painstaking and error-prone art form. These scientists were not just building computers, they were building elaborate facades, attempting to project an image of parity while knowing the foundation was crumbling. Their triumph was not in beating Cray, but in building something that worked at all, a victory of perseverance over physics, which in the ruthless logic of the Cold War was still a defeat. The comparison between the CDC 7600 and the Soviet BSM-6, or the later Elbrus-1, is a case study in divergent technological evolution. It was not merely a difference in speed, but a fundamental divergence in philosophy and capability. The CDC 7600 was a monument to integrated systems-level thinking. Seymour Cray controlled every aspect, from the logic of the processor to the plumbing of the Freon cooling system. It used silicon-based integrated circuits, packing thousands of transistors onto small ceramic modules. Its instruction set was lean and fast, optimized for the raw number crunching of scientific problems. Its cooling was a masterpiece of quiet engineering. The entire cabinet was a sealed, liquid-cooled system where freons circulated in tiny channels, boiling away heat from the dense circuits. This allowed for a compact, powerful machine that could be installed in a modest-sized room. The Soviet BESM-6, its closest contemporary, was a masterpiece of a different kind. It was a hybrid built from a mix of discrete transistors, diodes, and early microchips. It was remarkably reliable and had a sophisticated, scalable architecture for its time. But it was large, power-hungry and air-cooled. Its development was fragmented. The processor was designed by one institute, the memory by another, the peripherals by a third, all coordinated by a labyrinth of state committees. This led to bottlenecks and compatibility issues unknown in Cray's holistic approach. The gap, however, was most evident not in the supercomputers themselves, but in the ecosystem that supported them. S had a thriving commercial semiconductor industry, companies like Intel and Texas Instruments, driven by consumer and military demand, constantly pushing the boundaries of miniaturization and yield. The Soviet chip industry, focused on military needs alone, suffered from poor quality control and lagged a generation behind in photolithography and cleanroom technology. While the West moved to large-scale integration, LSI, Soviet factories struggled with basic ICs. Furthermore, Western supercomputers had sophisticated software, optimized Fortran compilers, vectorizing libraries, and advanced operating systems that allowed multiple users to run complex jobs. The Soviet software environment was far more primitive, forcing programmers to spend immense effort on basic optimization, further widening the practical performance gap. The result was a compounding disadvantage: slower hardware, less efficient software, and longer development cycles for everything that relied on computation. This architectural and industrial chasm meant that even when a Soviet machine achieved a theoretical milestone, its real-world utility, the speed at which it could deliver actionable results to a weapons designer or a cryptanalyst, remained critically hampered. The supercomputer was the silent, unseen forge of the Cold War arsenal. Every major weapons system that defined the era, from the minutiae of a rifle's ballistics to the global calculus of nuclear exchange, was increasingly born from a digital simulation. In the United States, the CDC 7600 and its successors were tasked with problems of almost mythical complexity. At the heart of it all was nuclear weaponry. Supercomputers ran Lagrangian codes, simulations that modeled the behavior of materials under conditions of extreme temperature and pressure that could not be physically replicated outside of an actual detonation. This allowed for the design of safer, more reliable, and more compact warheads. It directly enabled the MIRVing of ballistic missiles, a strategic nightmare for Soviet air defense, as a single incoming booster could now release 10 or more independently targeted warheads. For missile defense, supercomputers modeled the kill chain, the radar detection, tracking, interception, and kill assessment of incoming re-entry vehicles, a problem involving thousands of variables in real time. In conventional warfare, the impact was just as profound. Computational fluid dynamics, CFD, run on these machines revolutionized aerodynamics. The design of the F-16's blended fuselage, the shaping of cruise missiles to hug the terrain, and the radical lines of early stealth aircraft all flowed from billions of calculations performed in silence. Armor and anti-armor development shifted from field tests to simulations. Engineers could digitally model the jet of a shaped charge penetrating rolled homogeneous armor, tweaking the liner geometry and explosive composition to find the optimal kill mechanism. For the Soviet Union, lacking this capability, armor development remained a process of thickening steel and adding layers, leading to heavier, less mobile tanks like the T-72 and T-80. This computational prowess also created new forms of electronic and signals intelligence. The National Security Agency used supercomputers for cryptanalysis, chewing through vast streams of enciphered diplomatic and military communications. They also simulated Soviet radar and air defense networks, crafting electronic countermeasures and flight paths for reconnaissance missions like those of the SR-71 Blackbird. In the Soviet context, the absence of such powerful tools meant intelligence analysis was slower. Cryptanalysis relied more on human cleverness and luck, and the design of countermeasures was reactive, often requiring physical capture of Western technology to reverse engineer. The supercomputer gave the West a predictive edge. The Soviets were often left to respond to realized facts. For years, the true magnitude of the computing gap was obscured from the Soviet leadership by the very secrecy that defined both sides. The West, understanding the strategic advantage, guarded its supercomputers with stringent export controls under the COCOM agreement. The machines themselves were classified as weapons. Technical papers published by Cray and others were deliberately vague about performance specifics and architectural secrets. The Soviet intelligence apparatus, the KGB's Directorate T for Science and Technology, and the GRU was tasked with piercing this veil. Their methods were multifaceted. They ran networks of scientific and industrial spies in the US, Europe, and Japan, targeting semiconductor manufacturers and research labs. They engaged in aggressive technology acquisition, using front companies to attempt illegal purchases of advanced chip-making equipment. They also relied on the analysis of open-source literature, however sanitized, and on debriefing Soviet scientists allowed to attend Western conferences. For a time, this produced a distorted picture. The Soviets knew the West was ahead, but the assessments likely framed it as a manageable lead, something willpower and resources could overcome. The culture of the Soviet system also encouraged optimistic reporting. No mid-level bureaucrat or intelligence officer wanted to deliver the cataclysmic news that the core premise of technological military parity was a fiction. The moment of unambiguous truth likely came not from a single spy report, but from a convergence of evidence in the mid to late 1970s. The performance metrics of the CDC 7600 and the newly emerging Cray-1 became impossible to ignore or explain away. Defectors from the scientific intelligence world may have provided context. The most damning evidence, however, may have come from the Soviets' own attempts to copy Western designs. When they acquired plans or samples of Western microprocessors through espionage, such as the Intel 8080, and attempted to reproduce them in their own fabs, the result was the inferior, reverse-engineered ARM VN80A. The staggering gap in yield, performance, and miniaturization between the original and the copy was a physical, undeniable lesson. It proved that the deficit was not just in design, but in the entire underlying industrial and material science base. This was the report that landed on the desks of the Central Committee, a conclusion stating that the gap was systemic, generational, and widening. It was a realization that coincided precisely with a period of Soviet geopolitical overreach and internal economic stagnation, casting a deep shadow over the leadership's confidence as they prepared to commit the Red Army to a new, uncertain war. The stage was now set for a collision between a military machine planning a conventional brute force intervention and a conflict that would increasingly demand precision, adaptability, and real-time intelligence, capabilities their adversary was nurturing in the realm of silicon, but which they themselves could scarcely simulate. The climax was not a thunderclap on a battlefield, but the silent, final click of a logical chain, concluding in the minds of the Soviet political and military elite. It occurred in the stuffy, smoke-filled chambers of the Kremlin and the stark utilitarian offices of the General Staff throughout the late 1970s. The turning point was the moment the abstract, technical lag reported by scientists and intelligence analysts was translated into concrete, strategic vulnerability, and was directly connected to an imminent live operation. These were not dry scientific papers, they were alarm bells. They laid out in uncompromising detail how the American lead in supercomputing was metastasizing into a lead in virtually every domain of warfare. S-warhead miniaturization, enabled by simulation, meant their missiles could carry more payloads with greater accuracy. Another would analyze the new F-15 and F-16 fighters, whose radar and flight control systems depended on advanced avionics suites only possible with high-density integrated circuits. A particularly chilling assessment would detail the emerging American work on stealth, or low observable technology, explicitly stating that its development was wholly reliant on computational power the USSR did not possess. For Marshal Nikolai Ogarkov, Chief of the General Staff from 1977, a forward-thinking and technologically aware officer, these reports were a chilling confirmation. He had long argued for a military technical revolution, understanding that electronics, not just tank counts, would decide future wars. He now saw the theory made brutally real. The Politburo, under Brezhnev's increasingly detached and infirm leadership, received a distilled but still dire version of this intelligence. The message was clear. The correlation of forces, the sacred doctrine of Soviet military planning, was shifting in a fundamental way that their own industrial base could not quickly correct. The strategic nuclear balance was under threat from more accurate, more numerous warheads. Their vast air defense network, the pride of the Soviet military, could be rendered obsolete by aircraft it could not see. This realization created a climate of profound insecurity, a paradoxical blend of overconfidence in existing conventional mass and deep anxiety about the technological future. It was in this specific atmosphere of technological insecurity that the final decision on Afghanistan was taken in December 1979. The intervention itself can be seen as an act stemming from a traditional brute force worldview. a hammer being used because it was the only tool the leadership fully trusted. But the planning for the war's conduct and the expectations of its duration were subtly infected by the new awareness of weakness. The generals knew their communications equipment was less secure and less robust than Western equivalents. They knew their battlefield surveillance and targeting capabilities were inferior. The order of battle for the 40th Army reflected this. Overwhelming firepower, massed artillery, and helicopter gunships were tasked with compensating for a lack of precision and situational awareness. The plan was not for a nuanced counterinsurgency, but for a swift, decapitating strike to install a stable puppet regime, a solution that relied on political shock and awe, not computational prediction of societal response. The crossing of the Amu Darya on December 24 to 25, 1979, was the physical manifestation of this turning point. As the lead elements of the 108th Motor Rifle Division rumbled across the Friendship Bridge at Termez, they were watched not just by their commanders, but by the ghosts of those technological reports. The BMD infantry fighting vehicles, the T-62 and T-72 tanks, the Mi-24 Hind helicopter gunships flying overhead, each was a product of a system that could build them rugged and powerful, but could not digitally simulate the wear of mountain dust on their turbines or perfectly model the ballistic arc of their shells in high-altitude, thin air. The soldiers were assured of their invincibility. The senior officers privy to the broader assessments harboured a more nagging doubt. They were committing a force designed for the European plains to a mountain war, relying on a style of warfare that their most advanced analysis was telling them was becoming obsolete. The war had begun not with the first shot, but with the first chilling acknowledgement of a deficit that no amount of courage or artillery shells could fill. The true, visceral turning point arrived not in the corridors of Moscow, but in the harsh, radiant landscape of Afghanistan itself. It was here that the abstract Silicon Gap manifested in blood, metal, and tactical failure. The Soviet military quickly discovered that its technological shortcomings, underscored by those pre-war reports, were not just strategic concerns, but daily lethal liabilities. The first and most pervasive issue was in command, control, and communications, C3. Soviet radio sets like the R-105M were bulky, short-ranged, and used easily interceptable frequencies. They lacked secure encryption modules that were becoming standard in Western armies, a direct result of less sophisticated cryptographic computing and chip manufacturing. Mujahideen fighters, often equipped with commercially available scanners, could listen in on Soviet troop movements and air assault plans. Coordination between motor rifle units, artillery, and close air support was slow and prone to breakdown. This fog of war was thickened by inferior Soviet technology, granting the guerrillas a critical intelligence advantage. In response, Soviet commanders often reverted to landlines and couriers, or simply stopped communicating detailed plans, sacrificing coordination for security, a step back into a pre-digital age of warfare. Secondly, the deficit in precision and situational awareness became glaring. Soviet artillery, the god of war, relied on massed barrages from pre-registered positions. Advanced fire control computers for real-time mobile targeting were rare. Conversely, the Mujahideen by the mid-1980s began receiving from the CIA the first man-portable laser rangefinders and targeting designators. A guerrilla on a mountain ridge could now pinpoint a Soviet outpost or column with laser accuracy, allowing for remarkably effective indirect fire with mortars or later guiding in precision munitions. The Soviet army had no equivalent widespread battlefield digital targeting system. Their surveillance was largely visual, pilots in spotter planes or soldiers in observation posts. They lacked the sophisticated signal intelligence, SIGINT, and image processing capabilities that supercomputer-derived algorithms were giving Western forces. The enemy often moved unseen. Third and most symbolically potent was the avionics gap in the sky. The Mi-24 Hind gunship, a terrifying and potent weapon, embodied Soviet engineering philosophy. Heavily armoured, monstrously armed, and demanding immense pilot skill. Its cockpit was an analogue nightmare of dials and switches. Navigation in the featureless or mountainous terrain was a constant challenge. Provided Stinger missile, which arrived in 1986, was a product of the Silicon Revolution. Its seeker head contained a sophisticated microprocessor that could filter out countermeasures and home in on engine heat with terrifying reliability. The Stinger didn't just destroy aircraft, it destroyed the psychological sanctuary of low-altitude air dominance. Soviet pilots flying machines without advanced missile approach warning systems or effective countermeasure dispensers, again a product of inferior computational modeling for infrared signatures and dispersion patterns, became sitting ducks. The Hind, designed to terrorize, was now terrified. These battlefield realities fed back to Moscow in after-action reports and casualty figures, creating a feedback loop of disillusionment. The war became a brutal, open-air laboratory proving the scientists' worst fears. Officers like Marshal Ogarkov saw their theories validated in the worst way. His arguments for a high-tech transformation of the Soviet military were met with resistance from a conservative senior command and a Politburo unwilling to bankrupt the state further. The Afghan quagmire was simultaneously consuming the resources needed for such a transformation and proving why it was desperately necessary. The military technical revolution was happening, but it was being pioneered by the CIA, ISI, and the Mujahideen using Western microelectronics, not by the Red Army. By 1985-86, the turning point was complete. The war was now understood, at least by a key faction within the military and scientific leadership, as unwinnable under the current technological paradigm. The initial brute force approach had failed. The enemy was agile, informed, and increasingly equipped with tools that neutralized Soviet mass. The Silicon Gap had ceased to be a secret in a report. It was a sniper's bullet that could down a helicopter from 3 kilometers away, a mortar round that landed with uncanny accuracy inside a base perimeter, and a constant, whispering voice in the static of their own radios. The confidence that had propelled the army across the Amu Darya had eroded, replaced by a grinding awareness of systemic inferiority. The retreat, when it finally came, would be a retreat not just from a country, but from an entire way of war that the future had already left behind. The withdrawal of the 40th Army from Afghanistan in 1989 was a geopolitical earthquake, but within the halls of Soviet military science and industry, it was merely the loudest echo of a collapse that had been years in the making. The aftermath of the Silicon Gap revelation was a protracted, systemic unraveling that touched every facet of the Soviet state, accelerating its eventual dissolution. The Soviet response to the technological chasm redoubled in the 1980s, but it increasingly took the form of a desperate and often futile reliance on espionage and reverse engineering. The KGB's Directorate T and the GRU scored significant successes, stealing vast troves of Western technical data, blueprints for stealth aircraft, advanced chip lithography, radar designs. The most famous operation, Farewell Dossier, provided a treasure map of Western technological weaknesses, but also brutally outlined Soviet dependencies. However, stealing a blueprint is not the same as replicating the ecosystem that produced it. Soviet industry attempted to clone F-35 from the IBM PC-AT, producing the weakly compatible AGAT and ES-1940 PCs, to the F-15's radar, leading to the Sukhoi Su-27's N-01 radar, which was heavier and less capable than its inspiration. This copying culture had a fatal flaw. By the time a stolen design was deciphered, retooled for Soviet factories and produced, it was already obsolete in the West, which had moved on to the next generation. It was a race they could never win, locking them into a permanent state of catching up to yesterday's technology. The immense resources poured into these efforts were ultimately wasted, draining the economy while yielding systems that were, at best, passable analogues. The Soviet defense sector, the Voyenprom, was a state within a state. But the Afghan experience and the relentless pressure of the technological race exposed its core inefficiencies. The system was optimized for producing vast quantities of known, proven designs, T-72 tanks, AK-74 rifles. It was catastrophically ill-suited for the rapid, iterative innovation that the microelectronics revolution demanded. When the Politburo, under pressure from Ogarkov and others, demanded a new generation of smart weapons, precision-guided munitions, advanced fighter radars, digital battlefield networks, the Voyenprom buckled. Competing design bureaus fought for scarce, high-quality components. Software development lagged years behind hardware, which was itself years behind Western equivalents. Projects like the T-80U tank with its advanced fire control or the MiG-29's NMO-19 radar were compromises, using inferior domestic chips where Western ones were specified in the original stolen plans. The much-touted Elbrus II supercomputer, finally deployed in the mid-80s, was years behind the Cray II and consumed a room the size of a basketball court for a fraction of the performance. The industrial base was not just behind. It was becoming physically incapable of bridging the gap, creating a generation of weapons that looked modern on May Day parades but contained computational hearts that were weak and outdated. Perhaps the most profound aftermath was psychological. The certainty that had underpinned the Soviet system, the belief in historical inevitability and the ultimate triumph of their socio-technical model, was shattered within the scientific and military elite. The men who had stared at the CDC 7600 report in 1979 spent the 1980s watching their predictions of strategic vulnerability come true. They saw their best reverse-engineered chips fail in the dust of Afghanistan. They read the reports of Stinger kills knowing they had no equivalent to give their own soldiers. This bred a deep-seated cynicism and a crisis of faith. If the system could not win the decisive battle of computation, could it win the Cold War? This disillusionment trickled upward. By the time Mikhail Gorbachev came to power in 1985, advocating for perestroika, restructuring, and uskoreniya, acceleration, he was surrounded by advisors who knew the scale of the problem was existential. The technological gap was a key, unspoken driver behind his policies of disarmament and détente. Competing militarily was now recognized as a race the USSR could not sustain. The war in Afghanistan had been the bloody proof of concept, and its end left the leadership staring at a future they were no longer equipped to shape. The most ironic and strategically resonant consequence of the Silicon Gap was the manner in which it directly armed the Soviet Union's enemies. The CIA's covert aid program to the Mujahideen, Operation Cyclone, evolved from supplying World War II-era Lee Enfield rifles to orchestrating a deliberate, real-world beta test of Western microelectronics against Soviet hardware. This was not charity, it was a live-fire evaluation. The technological pipeline, coordinated through Pakistan's ISI, began with communication gear, secure radios, surveillance scanners, and direction-finding equipment that negated the Soviet communications advantage. Then came targeting tools, laser rangefinders and designators that allowed guerrilla mortar teams to achieve near-precision effects. But the crown jewel was the FIAM-92 Stinger missile. Its introduction in 1986 was a seismic event. The Stinger's smart seeker head, with its microprocessor-based proportional navigation system, was a product of the very computational prowess the Soviets lacked. It could distinguish between a helicopter's engine flare and a decoy flare with chilling efficiency. The psychological impact was greater than the tactical one. Soviet close air support, the linchpin of their counterinsurgency, was fundamentally altered. Helicopter pilots began flying higher, faster, and with less effectiveness. The cost to morale was immense. Here was the Silicon Gap, weaponized and placed in the hands of a peasant army. Every downed Mi-24 was not just a loss of an aircraft, it was a propaganda image beamed across the world, proving that American chip technology could beat Soviet jet engine technology. The final cold arithmetic of the war served as the ultimate audit of Soviet capability. The official figures, though likely underestimated, are stark. Approximately 15,000 Soviet soldiers killed, 53,000 wounded, and hundreds of aircraft and helicopters lost. The economic cost has been estimated at tens of billions of dollars, a hemorrhage the stagnant Soviet economy of the 1980s could ill afford. But beyond these numbers lies a more telling statistic: the asymmetry of cost. The Mujahideen, funded by a multi-billion-dollar covert CIA budget, could lose men and primitive weapons and continue. The Soviet Union, spending that same amount to maintain its 40th Army, was losing cutting-edge hardware it could not easily replace. Each Su-25 ground attack aircraft shot down represented a complex assembly of systems where inferior avionics may have played a role in its vulnerability. Every failed advance, bogged down by poor coordination and intelligence, represented a failure of C3 systems. The war became a brutal cost-benefit analysis, and the balance sheet, calculated with Western computational superiority on one side, proved ruinous for Moscow. The Afghan war, fought under the shadow of the Silicon Gap, delivered the final blow to the doctrine of strategic parity. When Ronald Reagan announced the Strategic Defense Initiative, SDI, in 1983, it was dismissed by many in the West as science fiction. In the Kremlin, however, it was received as a terrifying plausibility. SDI was a system that would live or die by supercomputing, tracking thousands of objects, making real-time interception decisions, managing a global sensor network. Soviet scientists, understanding their own computational limits, knew they could not build such a system, nor could they realistically simulate its effectiveness to develop a countermeasure. The fear of SDI was not of lasers in space, but of the computers on the ground that would control them. This technological intimidation campaign worked. By the late 1980s, the Soviet Union was a superpower with a hollow core. Its military was vast, but increasingly archaic in the metrics that mattered most: information processing, precision, and systems integration. The economic strain of trying to compete, of funding a hopeless war while attempting to reverse engineer a whole new technological era, was catastrophic. The Silicon Gap had morphed from a scientific concern to a military liability, and finally into an economic and existential crisis. The retreat from Afghanistan in 1989 was the first public admission of defeat. The collapse of the Berlin Wall later that year symbolized the end of an empire sustained by will and steel. The formal dissolution of the Soviet Union in 1991 was the final administrative acknowledgement of a reality long since concluded in the labs, on the circuit boards, and in the mountains of Afghanistan. A system that could not compute the future had none. The story of the CDC supercomputer and the shockwave it sent through the Soviet system is more than a footnote in the history of technology. It is a parable about the nature of power in the modern age. For decades, strength had been measured in tangible, brute metrics: tons of steel produced, megatons of yield, divisions of tanks, the thrust of rocket engines. The Soviet Union excelled at this language. It spoke it fluently, building monuments of mechanical might that dominated the physical landscape. But in the second half of the 20th century, a new, silent currency emerged. It was measured not in tons, but in transistors per square millimetre, not in thrust, but in floating point operations per second. This was the currency of abstraction, of simulation, of compressed time. The supercomputer was its mint. It allowed its owners to collapse years of trial and error into days of calculation, to foresee failures before they were built, to iterate in the realm of pure information. The Soviet scientists who confronted the CDC 7600 specifications were among the first to see the future with dreadful clarity. They understood that their civilization, for all its colossal might, was speaking the wrong language. The gap was not just one of speed, but of perception. The West was beginning to fight wars inside machines, optimizing reality before imposing it. The Soviet Union was still condemned to fight its wars in the unforgiving, expensive world of matter. Afghanistan became the tragic proving ground for this divergence. It was a conflict where the limits of a mass-production, brute-force paradigm smashed against the emerging age of precision, information, and microelectronics. Every Stinger strike, every intercepted communication, every failed offensive plagued by poor coordination was a real-world data point, confirming the theoretical models of inferiority written years before in those classified Moscow reports. In the end, the Silicon Gap was a gap in time itself. It represented the ability to think faster, to adapt quicker, to see further. A system that could not process the present with speed could not hope to navigate the future. The Soviet war in Afghanistan was not lost solely in the Hindu Kush Mountains. It was lost in the clean rooms of Silicon Valley, in the chilled cabinets of Cray's laboratories, and in the silent, despairing realization of those scientists in a bunker outside Moscow who held a piece of paper that told them they were already living in the past. The Cold War's conclusion was not simply a political or economic victory. It was a validation of a new kind of power, a power rooted not in the massing of force, but in the mastery of information. The last soldier to cross back over the Friendship Bridge from Afghanistan in 1989 marked the end of more than a failed intervention. He was the closing parenthesis on an era where might alone could dictate destiny. The future belonged not to the heaviest iron, but to the fastest thought.